neural network toolbox. So here is the normal description that I'm giving. So for neural network toolbox, deep learning concepts has been added. And it is being renamed as deep learning toolbox. So in this way, I'm having my own paragraph. So now I can go and I can describe about what exactly the previous neural network toolbox and how it is being converted to deep learning. So this is the complete documentation that we are having. Now I can have a code. So here I can go and I can say as new FF. So new FF will be creating a new feed forward network. So I can make this one to be a code. I can make this one to be a code. Or in other words, I can just do in this way. P equal to 0 colon 0.05 colon 2. Then y equal to humps of T. And I'm going with the new FF and I'm creating that one. So yesterday we have seen about this one. So now I'll do one more thing. So A equal to, without the termination, I will use this. And y equal to humps of T without the termination, let me use. So A over here, then I will have instead of y, the B variable. So without termination, I'm using. Okay. Now you observe coming down to .mlx file, some heading is there, some code is there, some documentation about introduction to toolboxes or there I've set. Then I'm having another code. Now without saving, I can run this file. Without saving, I can run this file. Let me run this file. By running, you can see towards the right side, the outputs has been collected. The peaks, when I have executed yesterday, has created this output. So let me use the command window. Yesterday, for the complete day, we have used the command window. If I'm going to type down peaks over here, generally this is what that is being executed and the output is available in this file. So here I'm going to close this. But coming down to .mlx, the same peaks, whatever the output, it is being displayed towards the right side and the output is available towards the right side. Similarly, when we are going to execute logo, the output is available towards the right side. And when I'm going with t equal to 0 colon 0.05 colon 2 with semicolon, there are no outputs. But when I'm executing a equal to 0 colon 0.05 colon 2 without termination, that's why the outputs are available over here towards the right side. So in .mlx file or the live script, we can have the documentation, we can have the code, and we can collect the outputs within the .mlx. Now I'll go and I will save this. While I'm going to save this one, make it sure the file name should be done as I said yesterday, whatever the rules. And here purposely I will do one more thing. So I will go with the demo underscore 1. Anyhow, I know the extension is .mlx. So purposely I'm doing this one. So towards the left side, I'm having these two files. Now let me clear everything. Demo underscore 1.m and demo underscore 1.mlx. These are the two files that I'm having. Now what I'll do is I will double click on .mlx. And as I'm going to open up, you can see even these output files are available. So let me right click and clear all the outputs. And I'm going to run the file once again. As I'm going to run the files, as we're able to execute, and this is the output that we're having. Okay, let me save this and let me close. Now let me open up this .m file. If I'm going to open up this .m file, and if I'm going to run, then immediately I'm having an error. I'm unable to execute. MATLAB cannot run this file because at so and so path, there is demo underscore one dot mlx which shadows this. That means within the current folder, if I am having .m and .mlx with the same file name, then I can't execute .m file. So there's a limitation over here. But I can execute .mlx. So then what can I do? I have to rename this .m file. So I'm going to right click and I'm going to rename. And here I can call this one to be 123. And if I go and if I'm going to run this, then I'm able to execute demo underscore 123.m file. So one important point, .mlx and .m, if both are at the same folder, then I can't run .m file. In other words, I try my level best to name .m files with one format and .mlx with some other format. So coming down to .m, if I'm going to go, then I can add 123. And if I want to use .mlx, generally I go with underscore 1, underscore 2, underscore 3, and so on. In this way, I can differentiate between .mlx and .m file. Now, there is one more advantage with .mlx. Now, let me say that I wanted to give some assignment to the student. Now, after going home, the student can write down their program in .mlx and they can execute the file. And after execution, they can save the file and they can share this file. And once they are going to share the file, then we can have the documentation and we can have the code, and also we can view the output directly within this .mlx file. So in this, we can have an advantage. So once I'm going to save the file and once I'm going to share this, then along with the documentation, the code, even the output will be available. No need of executing. I can directly view the output. So this is what that we can do. And coming down to .mlx. So if you're able to observe here, all the concepts are available where I can go with the title, heading 1, heading 2, heading 3, and also the normal. And also I can have the text format with bolded and so on. So whichever that is available, everything is available. Now, how exactly the documentation is available within the MATLAB? If I'm going to go back to the help, if you are able to view, it's the same thing that we are having. It's almost the same. ANS, which is in orange color, actually that one is a title for us. Then they're describing what exactly is this ANS stands for. Then they're going with the syntax, then the description, then examples, and so on. Now, Open Live Script. Today, let's focus our attention on Open Live Script. So coming down to the latest version of the MATLAB, which I'm using, we are going to have .m files, and also we are going to have .mlx files. Open Script, Open Live Script, both are available. So if I'm going to click on Open Live Script, the same program will be opened in the editor. Now I can go and I can run this file, by which now I can see the outputs. So here you can see, when compared to previous one, the outputs are available within line. 2 plus 2, answer equal to 4, result equal to 4 plus 4, result is 8, and answer equal to 4. So just I'm calling the variable with its name, answer, and here it says as answer equal to 4. Now let's switch over towards the right side within this editor. I'm having 3 options towards the right side. If I'm going to click the first option, then outputs are collected towards the right side. If I'm going to click the second option, then outputs are collected in line within the program. And sometimes I wanted to hide only the result I wanted to show. Then I can select the third option. Only the results I'm going to show. To give a better understanding, what I'll do is I'll go back to my program. So let me close this. I will not save this one. So here we are having .mlx. So already I've executed. Now these are available. Now, if I'm going to select the first option, the outputs are available towards the right side. If I'm going to select the middle option or the second option, the outputs are available in line with the program. Output of the peaks is execution of that mathematical equation, then the output, then logo output, then these variables output. And the third option goes in this way. I can hide the code and only display the results like this. Only display the results like this. So these three options are there. So whichever you want, you can use that one. So right now I wanted to use the first option where I wanted to collect the outputs towards the right side. Just I wanted to separate my results with my code and the documentation. Now, coming down the academic point of view, so we can use this one for our research work because the complete documentation we are able to provide at one instant. And also sometimes if we wanted to hide the code, we can hide the code and focus our attention only on the results. And also we can go ahead with the assignments also. Now students, they are going to write down why they are picking up these variables, why they are choosing these values and so on. Just they can have a description over there and they can execute the outputs and they can collect the results and they can share it. So in this way we can have. If the program is not being executed, then what we can do? So manually again, we have to open and we have to run the file. But anyhow, we can suggest the student saying that execute the program, collect the output, save it, and to share it. So in this way, we can recommend the students. So in this way, we are going to have many advantages. Now, one thing I'll do. I close this .mlx. I close this .mlx. Till now, whatever we had done are the examples that I have explained yesterday, but coming down to MATLAB, they have provided many examples. So within this documentation, within the MATLAB, you can see the examples. If I'm going to click on the examples, so there are so many examples that are available. So many examples that are available. I'll do one thing. I'll guide you how to use the user guide for the reinforcement learning toolbox. In today's agenda, we are going to discuss on reinforcement learning toolbox. So I'll guide you how to use the tool, the user guide to learn about the reinforcement learning and what are all the documentations that are there and what are the facilities that are there. And in the afternoon, I'm going to introduce you about on-ramp courses, which is a self-learning courses we are having. These are nothing but the training courses. So within 3 hours to 4 hours, we can complete these courses. And once we are going to complete the courses, we are going to get the certifications. So today, the complete documentation and also the resources that are available for the campus-wide, I'm going to explain you along with this one, the reinforcement learning toolbox. Now, first I have to go with the reinforcement learning toolbox. So for this, I'm going to help. There's a drop down and here I'm having documentation. If I'm going to click on documentation or a function key F1, then a new window is going to open up. A new window is going to open up. And here I go by product list only. In latest version, a new feature has been added, which says as category. But in 2021A, up to 2021A, only product list is available. Only product list is available. Now I go to reinforcement learning. So they are alphabetically being orderly placed. So I'll go to reinforcement learning. Reinforcement learning toolbox. Now this is the complete user guide. The same user guide is also available online. So those are not having laptop, just you can go down in this way. So I can say it as MATLAB reinforcement learning documentation. Then there are so many. So you can see control systems and so on, but here I'll go to products reinforcement. Products reinforcement. Now this is the documentation that we are going to have for the online. So you can access this. It has been placed in this way. Whereas I'm going to refer to the installed version of the MATLAB and the user guide that is available with this installed version of the MATLAB. So this is reinforcement learning toolbox. And exactly what we are going to do. So in reinforcement learning toolbox provides an app functions and assembling blocks for training policies using reinforcement learning algorithms, including Dukian, PPO, SAC, DDPQ. You can use these policies to implement controllers and decision-making algorithms for complex applications such as resource allocation, robotics, automation, autonomous systems, and so on. Now, before moving further, just I wanted to have an understanding. Have anyone worked on reinforcement learning? It's a very new topic. Okay, can I have the marker so that I can explain? I need marker. Anyhow, let's click on get started. So reinforcement learning, whatever the toolbox gives us the facility, it is being described over there. Now we are going to click on get started. Get started. Yesterday I have shown you about the apps and also the same from the generated simulating models. So all these are available even in the reinforcement learning toolbox. Just like yesterday, we have trained up. Over here, we are going to have the same concept, but this is somewhat different, where the models will be learned by itself. Yesterday, we have given the input and the output. Here, we are not going to give. Only the target we are going to give, and it has to learn by itself. So there's a major difference. Once we enter into the reinforcement learning, there's a complete different scenario. So I will use the whiteboard and I'm going to explain you about that one, but let's move it a bit further. And now let's click on what is reinforcement learning. Let's click on what is reinforcement learning. Below over here we are having. And if I'm going to click, this is the diagram that is very, very important for us. One, yesterday we are having the input and the output. Based upon that data we have trained up. Over here we are not going to do that one. Here, what we are going to say is we are going to award some positive values or we are going to give some rewards. Based upon the reward, it tries to learn by itself. The model itself has to learn by itself. So what exactly that we can do? So for this one, just to give you an idea, let's do one thing. Yesterday, I have shared one link. Now let's go to that link. Once again, I'm going to share to you. Sites.google.com view deep robotics and home HOME. So I'll share the link in the chat. Can I get the chart? Yeah, here I'm having chart. So this is the link that has been shared. Just you can go to this link. And here I'm having few examples. If I'm going to just come down. Okay, this is available over here. This part. This part. So this is being done by using reinforcement learning, but here I have done by using Python. Just to give you an idea, I wanted to use this as an example. Within the monitor, actually by using my mouse, I'm dragging that red color box. That is the target I want my robot to reach. So for this one, what we are going to do is, so now you can view to this video, whereas I'll go back to the MATLAB because for me, this is my reference. What exactly that is going to happen? This is my reference. Coming down to today's session, let me have an understanding. So what I'm going to do is, in yesterday's session, let me say, I wanted to create a NOT gate. I wanted to create a NOT gate. How exactly the supervised learning with artificial neural network will be working is in this way. I'm going to have the input over here and I'm going to have the output over here. Now here we want to perform the NOT gate. What is the NOT gate? We are going to use the binary. If the input is 0, output is 1. If input is 1, output is 0. So this is what. Now I want you to create an artificial neural network which behaves just like a NOT gate. Now what can I do? Coming to output, the input can be 0, whereas the expected output is 1. Right now there is no output, but the expected is going to be 1. This is what we are going to do. For this one, we are going to have something known as weight. W. We are going to have something known as weight. And now we are going to have the bias. Right now, I'm going to ignore this bias. There's something with this bias. I'm going to ignore. Now, for the input 0, value W, which we are going to choose, or which by training we are going to allocate some numerical value. W is the one where we have to find, or by training we are going to allocate some value. Or even it can be handpicked also. Coming down the output is nothing but input into the weight W. Right now I'm ignoring the bias. So output is nothing but input into W. Now if I'm going to have 0 over here, the expected value of the output is 1. What can be the W so that it satisfies? The W like a function. W is a numerical value. Take W as a numerical value right now in the NOT gate. Right now in the NOT gate. What can I do so that I can have 1 over here? Since it's already 0, make it sure that whatever the W value, it will be always 0. So my condition will not be satisfied. Fundamentally, it will not be satisfied. Okay, let me take another scenario. Let the input be 1 and the expected output is 0. What can be the value of W so that it satisfies? Here, there is one condition where my W can be 0. So if this is 0, then my output will be 0. Whatever may be the scenario of the inputs, if W is 0, output will be 0. Satisfied. But when the first scenario, I'm unable to do. So partially I'm able to create a NOT gate. Only one condition is still satisfied. Then can I alter this one? Yes, let's alter this one. Since I'm using in this way, let me make the things to be so 0, 1, let's represent as -1 and +1. Let's represent. Okay, so what is the logic we are going to have? If I'm going to have -1, then output should be 1. If this is 1, output should be -1. Now give something which is -1. Now the expected output is 1. Now what should be the value of W so that I can get so W can be -1. W can be -1. Similarly, if I'm going to give 1, output should be -1. Can be minus. So if I'm having W to be -1, then this condition will be satisfied. That means I'm able to prepare my own artificial neural network by handpicking this weight. By handpicking this weight. Now, if at all I wanted to go ahead with a little bit complicated gate like AND gates, but here beforehand we know the input and the output, and output we are picking. If I want to have the AND gate, then what is the logic? 0, 0, 0, 1, 1, 0, 1, 1, then 0, 0, 0, 1. Then how should the architecture? Always we are going to have the number of inputs based upon our data only. Now I can call this one as the data. So there are 2 inputs. So what about the output? Only one output. Now what we are going to do? So here we are going to have the inputs. Assume that this one is a neuron. So inputs are coming from here. We have placing a dash, it's nothing but we are assuming those are nothing but I'm inputting some data. Then what is going to happen? Every neuron will be connected to another neuron. And here we are going to have the weight. But since we are having 2, that's why I'm going to call this W1 and W2. What we are going to do? Here we are going to have input 1 and input 2. The logic is in this. Multiply now what can be the weights so that I can have the first condition should be satisfied. These 2 are 0, 0. Then what can be the weights so that now output will change 0. W will be 0. Okay. So when we have variable to accept W1 and W2 can be zero. Okay, oh, let's do one more thing. If I want 0, 1, and I want the output to be 0, then what can be? So here this is 1 and this is 0. That means they are going in a situation. I need these outputs based upon these inputs. The W1 and W2 will be only W1 and W2 with a numerical value. Whatever will be the input, output should be satisfied. They're not having multiple W1, W2s, only this architecture. Then can you do that one? At some stage it fails. That's what I'm going to do. Yes, a simple circuit will not sit for a bigger problem. That's what I'm going to do. Is they are going to have the inputs and outputs. There is no other alternative. But internally, they are going to have one more architecture where we call this one as the hidden layers. Anyhow, the logic is the same. You have to multiply in the same fashion. So each and every one you have to connect. So all three should come over here, and all three should go over here, and so on. So in this way, we are going to have the inputs and the outputs. So I1 and I2. Now we are going to have W1. So we are having first, second, and third. So W11, W12, W21, W22, W23. It's a many architecture. W31, W32. So making sure that we are going to choose these values in such a way that whatever will be the combination of the inputs, output will be according to our truth table. So it can be positive values, it can be negative values, it can be the value of 0, it can be the value of anything. So by training, what we are doing is actually we are picking up these weights. We are going to pick up these weights. We are going to pick up these weights. How we are going to pick up? Because hand picking is a little bit difficult for us. Moreover, since we are having the computer, why can't we use the for loops and why can't we write down our own algorithm so that we are going to train up in such a way that the weights will be just weights. Then, by the combination of the inputs, I'm going to have the associated output. That is only that we are going to do in the training. While doing that training, as I said yesterday, no system can be perfect. 100% accuracy we will never get. Then, what we are going to do? Here I'm going to do this. I'm going to have I1 and I2, then I'm going to have hidden layer. In anything, then I'm having an output. So inputs are there, hiddens are there, output is there. So here we are going to have the weights, is it not? Weights and the bias. What we are going to do? First I'm going to give some input value, some weights randomly we are going to pick. That's why I said. Each student, each person will be getting their own different. So what they're going to, how we have to start? Randomly, I'm going to assume W1, W2, W3, all those values, and I'm going to place it. Then I go with the mathematical calculation. Then I'm going to just check what is the output based upon my truth table. If the error is large, then I'll come back and I will adjust these things until the error minimizes. Until the error minimizes. So it is a repeated process. How many times I have to repeat and process that one? Actually, say manually going and doing this one only. That's why we choose the tip of saying as 1000 or even it can be 1 lakh once. It can be 1 lakh once. So whenever we are going to go and do this one, then we are going to come up with the concept known as training the artificial neural. So that is it. And what is the error that is accepted? Yesterday we have seen 10 to the power of -3, even 10 to the power of -6, 10 to the power of -9. UHS. Sometimes even it can be 10 to the power of -1. They are not going to power -1. They are going to do it. So this is what that we are going to do. That's why we used to have those 3 algorithms. Yesterday we have seen those 3 algorithms within the app. Those 3 algorithms are meant to go ahead and train up all. Okay, so coming down to yesterday's session, we have the input and the output. But some means we are able to come up with the ways we are able to calculate. We are happy. Now coming on today's session, what is going to happen is just I'm going to have the environment. So the block diagram is important. Just try to observe the block diagram. And here I'm going to have the policies. So let me take one example. My walk clock is there. Let me say my walk clock is there. And I'm having only one hand. So let me assume that this is one hand that I'm only one hand. Let me manage how I want it is or a second. That's all. Now, internally motor is been connected. Now the motor can rotate this one for 360 degrees. For 360 degrees. So now it has become an engineering topic. Now what exactly that I want to do? As I will go in, as I'm going to place my hand over here, that means this one I'm going to place it over here. Let me assume this one is the touch screen. Then I want my hand to come down over here. Or I can call this one as a heading. Okay, since I'm using my hand, so I can make this one as. Now in which direction it has to move? How many steps it has to move? Or in how many degrees it has to move so that it can reach my required position. But there are options. You can move in this direction or you can move in this direction. Is it not? Then if at all I'm going to make this one to be a servo motor. And actually this is to be a servo motor. Let me ask you. There is something. This is a servo motor. Then if I'm going to move in this direction, is it correct or how can I know? If I'm going to move in this direction, if it's correct or how can I know? We can't know. So now let me extend in this. Let me extend in this. What I will do is I will take a spin and one more and we have one more. Now let me say my robo is over here. My robo is over here. My ultimate goal is this is the starting position for my robo. Yes, and this is the finish. This is the block that I want to compensate block. This is the start position. Now my robo is over here. I want my robot to move in any of the direction with its own freedom, but ultimately I want this robot to compensate the motor. And let me assume that only it will be moving one step only. It has to move only one step. That means what we are having, ultimately I'm saying that there is some environment. I'm creating some environment. This is one environment, this is another environment. Then here I'm going to just say that what is the target? What is the target? What is the achievement it has to do? What it has to achieve? Just we are telling. So I'm asking this robot to come and settle down over here. And I'm framing some rules. What are the rules? It can move in any direction, but only one step. Only one step. It has to move. That's all, nothing else. And it has to finish. It has to learn by itself and it has to come down to finish position or end. Starting and ending. Now let me take this. How can it happen? It can move either in this direction or in this direction or in this direction or in this direction. Randomly it can move anywhere. Let me assume that it tries to move upward direction. Tries to move upward direction. Is it starts? It can move. Then, is my robot moving the right way or wrong way? Actually, it is moving away from my destination. That's why here what I'm going to say. I'm going to have the distance measurement from this position to this position. If I'm going to move away, the error is more. If the error is more, then I'm going to reward the negative points to it. It's a reward concept. I'm rewarding the negative marks. So when it is going to move in this direction, then it receives the negative value. Then immediately it tries itself to collect as many because we have learned it. Now robot has to do that one. Now let me consider. Already it has moved from this position to this one. Already it has taken a decision, it has moved. Okay. Now we are awarding a negative. Let me call it reward. So it has gained one reward, it is negative. We are going to have the policy that collect as much as positive rewards will be. Has to collect as much as positive rewards. Already 1 minus 1 is there. So then it understands that. That means algorithm thinks in such a way that, okay, if I'm going to move in this direction, since I'm getting negative, I should change my direction. Our algorithm are built in that way. Now what is the issue? Ultimately, there are three options. One, I can move in this way, I can move in this way, I can move in this way, whereas this has been eliminated. Is it not? So I can't take this one, though the option is there, I can't take. So again, if I'm going to move in this direction, which I'm moving away from it. Since it is random, if I can move in this way, again I'm going to award one negative. But let me just ignore this one to be very positive. Let me say that I'm going to move in this direction. Then I'm going to give one positive value. I'm going to reward a positive value. Then let me say my robot is right now over here. So since my robot is right now over here, then what are the decisions it can take? Since if I'm going to move in this way, it's the negative, I will not try to move in that way. I'm having the option to move in this way, and in this way. And since I'm going to have an option that since I have gained the positive, it can move in this direction. That means it's we are writing our algorithm. So if I'm going to move in this way, then what is the reward I'm going to get? Let me assume positive one. And now it is coming here. But if I'm going to move in this direction, the distance becomes even lesser. Then I'm going to be rewarding +2 or +5. So in this way, as we are going to write on, we are going to iterate. We are in a loop, trial and error only. So again, trial and error. The robot starts to move in different directions. Then as it is going to move in this direction, it is receiving negative. As it is receiving negative, it tries to avoid this direction. Then ultimately, what it will be doing? It tries to move towards this direction and downward direction. So knowingly or unknowingly, what is happening is, I'm able to come up with a conclusion saying if I'm moving up or moving towards right side, that means my left side, I'm getting negative. So I always have to focus my attention to move towards right side and bottom side. Again, we have the rule saying that this is the border, you can't jump over. Again, we have the rule, you can't jump over. So based upon this one, since it comes, let me say it has already come up over. It can't move, so it tries to move this way. Again, it can move in this way. Again, if it is going to move in this way, the negative, that's why it restricts itself. From here, it tries to come down over here, tries to come down, tries to come down, tries to come down, tries to come down. Then negative. In this way, try to reward our robot based upon its wish. And it learns by itself. We are doing nothing. We are doing nothing. It learns by itself. This is what it will be doing. Now coming down to this environment. This environment. Mostly benchtime first, mostly motor service, we have this here. So if this is the destination, it has to move. There are chances that it can move in this way, and there are chances that it can move in this way. Now, if I'm going to move in this way, what will happen? If I'm going to move this way, again, nothing goes on. But how many steps should I do? So from here, we are going to have a concept. From scenario to scenario, it changes. But in each way, we have to design our environment. So because if I'm going to move in this way, it's well and good. Again, I can move, again, I can move, again, I can move. Always I'm going to be faster. But let me just increase the complexity. And then we have 2 degrees of robotic. So the one that I'm showing in the video. So what exactly that is happening? With a single program, we are going to have a beautiful concept which says as I can move either in this way or I can move in this way. But if the target is over here, moving in this direction, now what is happening? negative and negative. That means I have to avoid and I have to move in this direction. A little bit simple to understand. This one and this one gives a simplest one. So I'm going to give the target over here. Then what will happen? This is the length of the arm. I can reach only this point. And if I'm going to give the target over here, can I achieve this? I can't. Because that is the length only can move in this way. That is only this border second. Only the perimeter I can whatever. So that's why let's do this. I will have a 2 degree of freedom nobody come. With different lengths we can have, but let me consider equal or different as a matter. Let me consider equal. Equal lengths. So L1 and L2 are the same. 1 meter, 1 meter, total 2 meters. Now, if this is 1 meter, usually it is going to attain only this part. It's going to attain only this part. This is the radius, 2 meters to this part. Now, this is 2 degree of freedom. If I'm going to give the origin as my destination, will that be? Yes, it can be like this, and this one can be 180 degree each way. By which second, I can get them. Two arms are there. So elbow and shoulder, shoulder and elbow. Yeah, I have that one. Only elbow means only this movement. Again, sorry, only shoulder means only this movement. Elbow also have it, then we can have all this. So that's why if I map this one, let's say I map this. Now, if I know I'm going to take all the translation, then I can cover all this area. Only with this one, this is the area that I can cover. With both the arms, I can cover the complete area. Okay. Now, can I give the XY coordinate to this one? So over here, we are going to have the XY coordinates. This is the origin 0, 0. Based upon your graph paper, I can have positive values and negative values. Then I can define this one to be 1, 0, 2, 0, 3, 0, 4, 0. Similarly, minus 1, 0, minus 2, 0, minus 3, 0, minus 4, 0, and so on. Based upon the coordinates, I want the end effect to come out. So what is left to me? So for this one, let me come up with this. Then this one base level. And it's a 2 degree experience for the car. And I'm giving the destination to give. This one is a little bit complicated. There are two parts over here. One, the shoulder and the elbow can take its own issue. The shoulder can move in this way, elbow can move in this way. Both can move in one direction. It's choice. But what it is, based upon its own decision as it is going to move, whatever the end effector, that end effector position will be calculated based upon this position, target position. So target position XY and end effector position XY. The error is more, then I'm going to reward negative. So it takes a bit more. It takes a bit more time for it to learn, but anyhow, it can learn. The only one thing is, yes, it can learn. Here, at least you got an idea that the possibilities are there. It is able to eliminate this side and this side. Is enough. But coming over here, it might be taking longer time, but yes, it can. And this is what I'm showing in the video. You're able to see. Actually, I'm moving that red color box with my mouse, and the hand is being moving over there. So it is being trained up by using reinforcement learning. Now, if this is the target, now let me say I'm having a robot which can walk. I'm having a robot which can walk. How to walk, we will not train. It has to learn by itself. It has to learn by itself. Then is it possible? Then, if I'm going to do, let's come down to the human beings. This was again the complexity. Let's come down to the human beings. Generally, the human beings moving forward direction. Generally. Sometimes we will move sideways, but very rarely we are going to. Now, if at all I'm going to have a 2 degree of freedom robotic arm is nothing but which represents my global limit. So feet I'm giving in this way. And here let's assume there are two hands. And yes, only observe the legs. It's a two-degree of freedom robotic arm. Now I want the robot to walk by itself. It has to learn, just like the small children will learn. Now I'm coming down to the technical. As a small child will be learning by himself, in the same way we want the robots to learn by itself. The only condition is if it is able to stand still and if it is able to move forward direction with both four fingers, 1, 1, 2, 1, 1, 4, then we are going to say there's no. Now, then it is. So what is what we are going to do? We are going to create our own environment, just like we are creating the environment over here. We are going to have the environment, the same way we are going to create the environment. What is the environment? We are going to say that we are having a man which goes by 10 feet by 10 feet, like this. And we are going to say that these are being fitted in such a way that this is right now standing in a straight direction. So it is standing directly standing on the feet. Directly standing on the feet. Now I want the robot to move in forward direction. What can I do? So randomly it goes and do some action, it may fall down. Randomly it may do some action, it may fall down. By which we are going to say that we are rewarding the negative value. The ultimate goal is has to collect as much as positive values. Then again, let's make the robot stand still. Again, it takes some action. So in this way, we keep on doing. Ultimately, it understands how to move its feet. It's a trial and error. It will be always falling down. Just you assume that it is going to fall down. But still, we are going to make it to stand. Again, it tries something. Again, it falls. But ultimately, after some time, it tries to understand something, saying that based on the environment, to stand over here and to move in forward direction, I have to do some action. That's what we are going to. So from the simplest to the complexity, as you can see. So all this we can do. In the same way, I can have a robot which can navigate from point A to point B without giving any observations, without saying anything, only about the environment they're going to say and the policy they're going to say. So now try to understand what is reinforcement learning. Observations are there and action is there. Now right now what I said is about the action. Based upon the action, what reward will be given to it. Generally, starting it will be negative rewards only, but it tries to, when it's algorithm, or how we are designing is try to collect as much as possible result. And environment we are going to declare, and then it is going to have its own observations. And here we are having the reinforcement learning algorithm, and we are going to create the policy. We are going to create the policy. Now, generally, if I'm going to apply to the real robot, we have done that one. The real robot will be ready. So whichever is the easiest one, just try to understand that one. So since we are at the starting stage, let me do one thing. I wanted to introduce even an obstacle. This is the simplest one. So let's use this one. Let me introduce the obstacle, and based upon this one, let's have a problem statement, the environment policy, and so on. So what exactly that we are going to do? First of all, is it clear up to here? It has to learn by itself. That is what the reinforcement learning. Let me say I'm having the environment in this way. Let me have the minute boxes. So this is my environment. We are creating our environment. For robot, I understand that is its own. For robotica, that is different. competition is there, the macro mouse competition. That is maze, solving a maze problem. Same is how to reach that position. They will give you one trial and two trial, and they reinforcement learning. I think the same thing will get almost similar. Some of the same. But they have not implemented this one. If you already search for reinforcement, then you have got the trigger, then it's okay. But generally, long ago, it's still available, which is just for the distance sensor based on the network. If you're searching for reinforcement, that's the okay. So quantity to quantity, it's the same thing. Coming to that. So what I'm going to say, I'm having such an environment, and after that, I'm going to say that it has to move from quantity to quantity. Quantity to quantity. So this is the destination. And this is the starting. The start. Okay, let me assume that the logo is over. Now here I'm going to place the obstacles. So whichever the box the most is consisting of the obstacles. You can have the obstacle in this way. That means if I'm going to move over here, anyhow we are going to avoid this part. We are going to move this way. Again, obstacles are there. The obstacles are there, then we show how to again avoid and how to move and how to fix this. Instead, you can create the obstacles. So it has to be. So when compared to previous, this is a little bit different. But that's the number. So coming on to reinforcement, we are going to what we are going to do is once I'm going to purchase the reinforcement, the algorithms which are very standard, over those algorithms we have provided for us. Those algorithms we are going to use and we are going to implement them for anyone. Now, what is the advantage in the toolboxes? No need of rewriting our algorithms. But if at all you want to have your own logic, you can create. So that's what I've done is I have used the Python and updated that one and I will go to. So that is the one that has been demonstrated in J2 Hackathon.
But sir, these things is not legible online, sir. Because 17 participants. Oh, you done now. That's it. Okay.
So in this way, we can create our own environment and we can create our own policies, the rules, and the limitations. That means these are the borders. This is what we are going to do. So about yesterday's complete data we are giving and we are training the actually we are adjusting the waste that is something for the training part. The fires are not concerned for simplification. And over here we are going to have this reinforcement. So let's take one example and let's move forward. So let this one be our reference.
So it's a supervised or unsupervised.
A reinforcement learning.
And there will be breakup, some kind of breakup, I think.
This is different, sir. They resemble to be same, but completely different. Just you see, if I'm standing, I have to walk. What should I do so that I can make my robot to walk? In supervised, we give all those parameters and we train it. Here, there's nothing. It has to learn. How many times it falls, we don't know. Will it learn or not? Also, we don't know. At least over there, the weights are there. Something adjustment random we are going to. At least we know something will be happening. But here, you can't say. Reinforcement.
In MATLAB, we can do simulation.
Yes, sir. Yes, sir. This is what I'm going to show. We can do the simulation. Okay, up to here about the theory concept. In the same way, we are having different concepts also. So not related to MATLAB, but coming out other things. We are going to have the apprenticeship learning. What is known by apprenticeship? Any idea? Or internship?
To work, we have to learn.
So coming on to actual, there's no internship. Actually, based upon students have used that word. Apprenticeship is there. That means some data they will give. Before entering into industry, what is apprenticeship means? Beforehand, for 1 year or 6 months, we say that we will be the trainee for 6 months. What are the work that is happening over there? Let me involve over there. Even they are going to permit us. So we are going to observe how things are happening and so on. Based upon that one, for future job application, it will become easier for us. That is apparent. That means some data beforehand I can give. Even that one also we can provide. So
Reinforcement.
so if I move in this way, gradually, yeah. If I move in this direction, then it becomes a supervised almost. Actually, there's a difference, but still.
Unsupervised combination.
So in this way we can have. That means why we are gathering all this technology means they're giving good results. Because always training a model to move from position to position, from position A to position B, feeding all the data, sometimes it's not possible. Because Mars rover, just we are going and dumping it. We don't know. We don't know exactly. Just we assumed saying that based upon few of the images, based upon might be 30 days data, 30 years data, we assume that if I'm going to drop over here and I want this robot to move from point A to point B so that our task will be fulfilled, then just blindfoldly we are leaving that one. So it will be driving by itself, where we are going to decide the parts from ground level, saying that commands will be given, it will be moving this way, it will be collecting the data. But if at all we can make this one to row by itself, how good it is. So the challenges are there. It has to learn by itself. It has to learn by itself. So there are few scenarios where we want the robots to learn by itself because even we too don't know those environments. Then it comes into an application. In the same way, if I'm in a forest, if I'm going to live, how can I cross the forest and how can I be in the city? It's a challenge, is it not? And if it is a robo, it's a big challenge. Let us assume that the robo is too costly, then it's really a very big challenge. But still, it has to learn by itself. So that means we are focusing attention. How can a robot learn? What are them? How can I design my algorithms? It becomes a research work. It becomes a research work. So in this way, we can do. It's not a, but we are having one concept. Deep mind. Google's deep mind. Deep mind. It plays with the that coins will be placed over there, white and black. So deep mind. So many competitions are being placed over there because we wanted to improve the algorithms. Because when it fails, really we don't know. Just to gather the information, we put the competition, we gather the information. Based upon that knowledge, again we write down our algorithms. Why we do all this? We have to write down the algorithms. And ultimately, our world will be evolving in such a way that we will not train up the robots. It will be trained by themselves. And one more concept. Integrate AI, ML, and IoT, it becomes a bigger system. Becomes a very bigger system. So on the end of the final day, I'm going to explain about those things. So let's discuss about this part. So as one of the application, my video shows you about the reinforcement learning. So this is being done by using Python only. So as I'm going to move, I'm able to make my robot to position its end effector at the same location. Just you can see. That means shoulder angle and elbow angle we're able to measure. And since the servo motor can't give 360 degrees, I'm using 2 servo motor. Okay, so over there even I can use the stepper motor, but still I'm going with servo motor because students are very familiar with servo motors. So in this way we can train up. But randomly, if it is going to move, then how it will be? Do you know? Randomly, at the starting step when we are going to train up, do you know how it will be? It moves randomly in this way. Though the target over here, we never expect that this will be moving over here. It moves like this. It throws itself, all the 2 angles. So all zigzag happen, but after some time it figures out. Then it comes to a observation saying that okay, this is I have to eliminate the negative values. Okay. In this way it can understand. Just you can see it's the Python, actually this is the MATLAB code. Now I can't show that one. So we can exactly know that after 15 to 20 minutes, it can settle down itself saying that these are the angles. One angle, another angle it can follow, and exactly it is going to mimic our target. So that's a good observation. Okay, so for this one, let's go to MATLAB. And let's visit ourselves to the reinforcement learning. And here, These are the steps that are involved. Formulate the problem. So here I have formulated my problem. Then create the environment. So different environments I have created. Then define the rewards. Over here I have just rewarded with 1. It can be 5, 10. So if it has already collected some X amount of the rewards, then I can make that one to jump if the obstacle is there. And this also we can give. Then create an agent. Then train the agent, validate the agent, deploy the policy. Okay. So just go through the documentation once so that we can take up one example that is available within the documentation. Now let's go with examples. Let's go with examples. Let's go with examples. In this one, I go with reinforcement learning, the examples. There are so many examples. There are so many examples, but at the first instant, I wanted to take you to the controls example. To simplify the things, let me take one example which is related to controls. Yeah, here. Train DDPG agent to swing up and balance cart pole system. This one, the red color. This one. Train DDPG agent to swing up and balance cart pole system. So let us double click, by which you are going to open up the complete example. Now you can go through this one. So there are a lot more things to be observed, but I will explain you in this way. Actually, this one turns up to be a PID controller for electrical, mechanical, electronics. We are having PID, so we can have the PID. CSE, they don't have PID, but let me explain. So for this one, so can you arrange 1 second, please? I'll use the. So once you are familiar with PID, now it is easy to understand. And this is the example that explains. Because programming, I will not go in there because it takes time. So now, as I have taken the one-to-one example, now let's take the same example. It's 1 degree of freedom. So it's 1 degree of freedom. Now it can rotate 360 degrees. But we want this rover arm to, or a pole, say we call this one as a card pole, just a pole. So I want this one to stand over here and balance itself. I want this one to stand over here and balance itself. And what can I do? Just I will start to swing. Because I have to overcome the gravity. So little bit more. At last, I will come down over here. Then be sure I may fall down also. Because I have to balance myself. So if I move a little bit extra, then I may fall down. Again, I will be over here. Again, I'll start to swing. Afresh, I'm going to start to swing. So I'm going to make it sure that as I'm going to swing, be sure there will be many failures. So for this one, to eliminate the failures, I can use PID. I can use PID. Can use the PID command. So what exactly that is going to happen? As I'm going to swing, so just for explanation, I will use the simplest words. As I'm going to swing, over here, I wanted to maintain this angle. Perfectly, I have to maintain this angle, but due to gravity, it must move in this way. So I will apply the PID control by which I am going to adjust. So for this one, we can have the sensors, or I can have some concept like this, or a microcontroller where it is going to take care of all those. But let me say that as I'm going to approach this position, and if I'm moving further away, then I'm going to give a reverse action. And if I'm going to move a little bit more, again, I'm going to give a reverse action, and this way I'm going to balance myself. This is the control by which I can balance. Even I can have a four-wheel cart, and I can have this one also. Now to balance this one, we can move this in either direction and we can balance. So many concepts are there. This is one of the concepts which goes with PID, but we are using reinforcement learning. So coming down to the reinforcement learning, now let's execute. The cart pole example we are using, and this one example is so let's take this example as our reference. And everyone, let's execute. So open live script. Open live script.
Main display.
Which one, sir? What should we do? Somewhere we have to tap on the 6841.
Window is visible.
My window?
Yes, yes, in visual, sir. You can go on.
I can go ahead. Okay, so for better understanding, let us take this example, but this is related to electrical, mechanical, electronics example. But for understanding, let's take this one. So this one turns out to be the Simulink model. So what I'll do is I will go and I will run this step by step. So top above, I'm having run in advance. As I'm going to click on run in advance, I'm going to open up RL card polls Simscape model. So for the first instant of the time, it takes around 2 to 3 minutes to open up the model. Anyhow, the model will be opened up. So let's wait. So towards the left side, we are having Simscape, Cartpole, TDPG example. So this is the example we are executing now. And this is the model. Yes, MATLAB code. Once again, I will show. So I will close this one. I will close this one. So how to get to this example? Once again, I will show. So I'm going to documentation. From start, I'm going to documentation. Then I'll click on product list. So those are online. So you are going to have category and product list. I'm going to product list. Then I go down to reinforcement learning. Reinforcement learning toolbox. Then here we are having examples. Click on examples. All the fully running examples are available. Now I go down to a particular example which says as train DDPG agent to swing up and balance cart pole system. So I click on this. The complete example is available. Now I'm going to click on open live script. Open live script. Since I have already used, that's why some editing it is asking. Just I'm going to say it as no. For you, it will the normal way of opening up. Now this is the complete model that we are having. So what I'm going to do? First, I'm going to open up the Simulink model. So this is the Simulink model that we are having now. This is the Simulink model that we are having. So anyhow, let's see about the output only. That's why what I'll do is I'll focus my attention only on the program. because from program also we can simulate these models. From program also we can simulate. Then here we are going to create the environment. Then the observations. And then we are going to declare the time. Then here comes the random generator. So the CD0. Then this is the agent. Then let's plot one graph, which is the layer graph. So here comes the workflow. Then I will go and I will come up with the options. Then we are going to have the algorithm or the function. Then the network. Then the options. With this one, we are going to create reinforcement learning DDPG agent. Now to train up, we are going to have the training options and also the plotting. So up to here, what we have done is we have set up our environment and also the agent and so on. Now, ultimately, we'll be going and we'll be simulating this one. So I will run this. A new window is going to open up. And that window will be docking onto the editor. And it has been fitted directly, but as it has to move upward direction, we are going to lose some visualization. So right now it has swinged, it has moved up. And once it has been moved up, it is able to balance.
Kind of things.
Again, we have to go back. So this is their example. Let's search about that. So right now, as reinforcement learning is working good. Reinforcement learning is working good. Okay, let me take one more example, then I will discuss. Let us close this. Let me close this one also. As I'm going to close this one. Then I'll go back and I'll pick up one more example. So here we are having quadruped robo locomotion using DDPG agent. So this one, this example, I'm moving my cursor, just you can observe. This example, let's take. This example, let's take. And if I'm going to click, the complete example is going to open up. Now here you understand the hip joint and the knee joint. Totally 4 legs. And here we are having the torso. Okay, let's use this one for our understanding. And I'm going to click on Open Live Script. Open Live Script. Now again, this one is a Simulink model. Because in Simulink, we are going to have the animations. That's why I'm using the Simulink. So let me just go ahead and let me run step by step. So here I'm clicking. So this is the robot that we are having. Now let me go back to my program. And let me create the network. Let me plot. Specify the training. Now I'll go with simulation part. So now here you can see. So sometimes the smaller step, sometimes the larger step. And it is able to walk. But here there is one thing, how it is learning, how it is falling down, all this we are unable to see. Only the final output we are able to see. Only the final output. Then what can we do? Okay, let's do in this way. Let's imagine. So right now we can't alter this program because, okay, online if they alter, what will happen? I don't know. An object. So coming down to the installed version, if I'm going to alter something permanent, it will be saved. That's why I will not alter, but I will explain you. So here, while I'm going to train up, because training part is most important, because it has to learn by itself, is it not? So while it tries to walk, sometimes it may be walking in backward direction also. Because as it is going to move, it may happen that it may move in backward direction or it may fall down also. Because there's a path that has been predefined, so it may fall down also. As all this scenario is going to happen, we are going to reward the negative values. So it falls down, it's move forward, move backward, move sideways, and so on. So all this is going to happen. So here we are going to eliminate. Let me say that it will not fall down, but anyhow it will be moving sideward direction, backward, and front direction only. Let me assume. Let us restrict to one limitation. It will not fall down, but anyhow it will be moving in forward, backward, and sidewards, left and right. Now, as it is going to move backward, sideways, then generally we are going to give the negative rewards. And if it is moving backward, we are going to give more negative rewards because the path is defined. Even we know from where to where this robot is walking because there's a slope. And already we have visualized this one. So we know the destination. It has to move in forward direction. If it is moving backward direction, generally we are going to give more negative, sideways, less negative. In this also we can define our algorithm. Then as it is going to move in forward direction, then it resembles that it is attaining the positive rewards only. So that's why while we are going to simulate, this is the output that we get. So already it is been trained. Already it is being trained. Okay. So now, generally to go ahead with the examples, we are going to have many examples. Among these many examples, we are going to start from the basics of the fundamentals. So here you can see I'm having the MATLAB environment and the Simulink environment. Both are separated. I'm having MATLAB and the Simulink, both are separated. So generally for focusing attention only on the output, we use the Simulink, but we are having the MATLAB functions also. So now let's open up only the MATLAB. So here I'm having create MATLAB environment using custom functions. Create MATLAB environment using custom functions. So it's a Carpo visualizer. And let's open up. Now the advantage with the user guide over here is as you are going to open up, even your path will be changing. And coming down the online, the associated files will be copied down to the MATLAB drive. Automatically it copies the MATLAB onto the MATLAB drive. So all the required files will be available for you. Really, they are going to be available for you. And if you're able to see, we are having .m files and .mlx files. These two files. .mlx is our main program and .m are the supporting functions. So how to create the functions? So let me clear everything. Let me clear everything and I'll go to home and I'll go to new script. And to define our own function, we are going to have the keyword which is function. Just to see what I'm doing. It has taken .mlx, I hope. Just give me a second. Let me close all this and let me start afresh. Which one? .m stands for MATLAB file. For live script, we are having .mlx. In the morning, I've explained about .mlx. So here to create a new function, what we are going to do is I'm opening up .m file. So it's on editor. Then I can say it as function. Function is a keyword. How many keywords are there in MATLAB? To know that one, just you can use command window to execute single instructions or single functions then and there. Then you are going to use command window. But generally, we will not use the command window. We go with editor, save the file, and we are going to use it. But sometimes command window plays an important role. So here I can say in this way. Is keyword. Just I'm typing down is keyword within the command window. Then MATLAB displays all the keywords over here. If you are going to count, we are going to have 20 keywords. There are totally 20 keywords. Break, case, catch, continue, else if, and so on. And among this one, function is a keyword. All keywords will be denoted with blue in color. In editor, all the keywords will be denoted with blue in color. So function followed with outputs, let me say x comma y equal to name of the function. So coming down to over here, we are creating a road function. So we should not use the function name which is available within the MATLAB or the MATLAB inbuilt function. We have to make it sure. Since yesterday I have said that all MATLAB inbuilt functions are with small letters only. So I'll make it sure that my function names will be consisting of the capital letters and the small letters in combination. Okay, I'll make it sure that my function name will be capital letters and small letters. And yesterday I have said small a and capital A differs. In this way, without knowing all the inbuilt functions, at least I can have my own function. So that's why I'm going to call this one as my function followed with inputs in the parenthesis. And let me call this one as a comma b. So function followed by square brackets outputs to name of the function, then followed by the inputs within the parenthesis. Multiple inputs, multiple outputs, separate them with the comma. Then let's define our function, what our function will be doing. X is nothing but addition of the inputs A and B. And Y is nothing but product of the inputs A and B. Then I'm going to use the keyword end. End is optional, but let's use the end because we can know where the function is starting and where it is ending. And here I will go and I will save this function. While I'm going to save, just observe. Whatever the function name that we are given, it tries to save with the same function name. Here we are having my function. Don't edit, it should be the same. Now I'll go and I will save it. Now towards the left side in the current folder, you can see my function with a completely different icon. Functions, visually we can differentiate from the .m and .mlx. Visually we can differentiate the function from the .m and .mlx. So this is the function that is available within the current folder. I can call this function from the command window or from different file. I can call this function from command window or from different file. Okay, let me use the command window because we can view the outputs. So I'm calling the function my function, and let me give the values which says as 10, 20. I can give directly the numerical values or I can supply the variables also. Either way I can do. And since it is giving me two outputs, let me collect those two outputs into my own variables. And here I'm going to call this one as x comma y. So I'm collecting into x comma y. X is nothing but summation of 10 and 20. Y is nothing but product of 10 and 20. Now let me execute. So what we are exactly doing, we are calling that function, my function, which is available within the current folder. And also we are supplying 10 and 20. And the function has taken this 10 and 20 and it's calculated the x value, which is summation, and y value, which is product. So by which we are having x equal to 30 and y equal to 200. But internally, this x and y and this x and y is differ. Just to minimize the confusion, I'm using this x and y only. Let it be. Now, let me go and let me supply only one input. I want to supply only one input. So the function expecting two, I'm supplying only one. Then be sure here there's a problem. Because while calculating x equal to a plus b, since there's no another input, so it is facing a problem, so it's an error. That means supply as many number of inputs as the function is expecting. Supply as many number of inputs as the function is expecting. Then what about the outputs? Without collecting the outputs, I can execute. Nothing goes wrong. So if I'm going to just call the function, give the inputs, still it executes. But there is only one variable to collect, so it is collecting only the x value. It's unable to collect y value. But as a good programmer, what we are going to do is we are going to always collect our outputs into our own variables like x and y. If I don't want to collect, then I can use this symbol. Only y we are going to collect. Or I'm going to collect only x. Or if I don't want to collect either, then as a good programmer, I have to use this syntax. I don't want to collect both the outputs, so this is the way that I have to program it. So don't leave it assigned because answer will be used. So if you don't want to collect, use this syntax. So this is the function that we have created just now. So functions are with .m files. In the same way as I'm going to the example program, let me close this. So in this one, create MATLAB environment using custom functions. Let me click on this. Now let me click on open live script. Now MATLAB opens up and it will provide you all the supporting function files. Whatever that are required, they will be available. So even in online, these will be available for you. So right now we are with the .mlx file and we are calling .m files. So here, when compared to the previous one, as the pole is hanging down, we made it to move forward direction. It is able to stand up, and over here it's not like that. We wanted to balance. Sorry, it is standing, but we wanted to balance it. To balance this one, we can move the cart pole. So it has been mounted on a cart pole. So on a cart, so this cart can move in forward direction or in backward direction. So by which we can balance. The training goal is to make the pendulum stand upright without falling over. So that is the goal. Now here comes the practicality. We are having the degree in radians and the downward hanging position is pi radians. Due to gravity, if it is going to fall down, it ends up at this angle. If it is standing still, then that is the angle. The required or preferred angle is only that one. A small variation, as you can make it sure that we have to bring back to theta only or 0. The pendulum starts upright with an initial angle that is between minus 0.05 and positive 0.05. So here we are initializing. The force action signal from the agent to the environment is from minus 10 to 10 newtons. The observation from the environment are the cart position, cart velocity, pendulum angle, and pendulum angle derivatives. The episode terminates if the pole is more than 12 degrees from the vertical or if the cart moves more than 2.4 meters from the original position. That means there is a limit. A reward of positive 1 is provided for every time step that the pole remains upright. A penalty of minus 10 is applied when the pendulum falls. Now we are moving a little bit in depth with the problem itself. Okay, already it is under the influence of gravity. Already it is under the influence of gravity. Is it not? Yes. So now let's move. Observations and action specifications. The observation for the environment are the cart position, cart velocity, pendulum angle, derivative. And whatever the states, we are going to collect those states. Right now, how the pole, how the cart will be. So that is the state right now. What is the action? So whatever at the particular instant, there is a state. So we are collecting that states. Then the environment has a discrete action space where the agent can apply one of two possible force values to the cart. So who is applying? Who is applying? The environment has a discrete action space where the agent can apply. That means I have to take an action. So it's we are going to apply. I want the robot to move in upward direction, sideward direction, left or right or down direction. So it's we are going to move. That is nothing but the agent. And there is a discrete value where with what force I'm going to move, -10 or +10 newtons. Over there, how many steps to move? 1. Over here, this is the force. So -10 and 10 we are giving, and cart pole action. Then from more, they were asking over there. So now create environment using function names. So my reset function.m. So when you are going to do this one, type what will happen. Just I will show you. Let's do in this way. So if I'm going to use the command window, type space some file name, and if I'm going to press down the enter key, then immediately it shows me the internal details like this. So my reset function, we can view in this way. If not, towards the left side, we are having the function. You can double click, you can open up and you can view. It's the same. It's the same. And if I'm going to do one more, let me say in this way, type space abcd.m. And if I'm going to click, be sure since it is not there, so it is not opening up. Then if I'm going to go and if I'm going to remove this .m, still. So that means whatever the function that is there manually to open up, you can open up. To display, you can use type. So why they were asking type my reset function is just to view that one. Then we are going with visualization of my step function also. And so on. Then here comes one more function, which is my step function 2.m. Now create the structure that contains the environment constants. Now you can see the gravity we are declaring, the mass cart we are declaring, the mass pole we are declaring, the length we are declaring, and maximum force. Our environment. And also we are coming up with the penalty also. So penalty for falling is -5. It's a custom function. So everything is being given over here. This will be handy for us. And once we are having, now we can go and we can run this. Okay, let me run the complete program. Anyhow, this is available with us. So let me go and let me run the complete program. And let me view. And all the variables has been created within the workspace. And also you can see the outputs over here. So here we are not having the animation. Just try to observe only the values we are getting. Only the values we are getting. So coming down to the animation, generally we go ahead with the Simulink because for Simulink with the Simscape and other toolboxes, animation is inbuilt internally. So that's why we use the Simulink. Okay. So generally to learn such a new concepts, it takes time. So that's why what we are going to do over here is we are having one new feature which is known as on-ramp courses. So everyone can learn MATLAB and the toolboxes by using on-ramps. So it's a self-learning training program that we are having, which is known as MATLAB on-ramp. So let me introduce you about the MATLAB on-ramp. And in the afternoon, we are going to do reinforcement learning on-ramp. And yesterday I have covered one topic, so artificial neural network. Anyhow, that topic is not available. It's available as deep learning only. So from tomorrow onwards, let's make sure that in the afternoon session, we are going to complete one on ramps. Okay. So this will be better for us. Now I'm going to introduce about MATLAB on ramp. To go to MATLAB on ramp, just go and browse saying as MATLAB on ramp. If you are not good with MATLAB, still you can learn the MATLAB. All the students and all the participants, if you are not good with MATLAB, still we are having a training program which is known as MATLAB on ramp. It's a free training program that we are having. It's a self-learning training program. For this one, just MATLAB account is necessary. That's all, only MATLAB account. And if I'm going to click MATLAB on ramp, then here I'm having MATLAB on ramp. If I'm going to click on this one, then this is the page we land up. This page we land up. And let me just click on details and launch. Details and launch. So this is the complete course overview that we are having and also the topics. But let me go to course overview. Then I'm going to click on model. So for this one, MathWorks account is necessary. So I will log in over here with my company account. So in MITS, every faculty, every student can use MATLAB and all these courses, everyone can use. It's free of cost. Only one requirement is you have to create the MathWorks account. Again, it's free. Everyone can create the MathWorks account. And once you're going to create the MathWorks account, then you can access all this. So I will click on Start Module. Then here I'm going to click. Are you getting the audio? Okay, here we have the audio.
Throughout the course, you'll be interacting with the Facebook inside our training center. How this might be
so it's a self-learning. It's a self-learning training program that we are having, so we can use this on ramp. And there are many courses. So let me introduce about the MATLAB now. And in the afternoon, we are going to do with the reinforcement learning. Okay, so let me click on next. So here towards the left side, we are going to have the task. The middle window is the one where we are going to execute. Towards the right side is the workspace. And here, if I go with the task, it says as towards the left side, you can see there's a blue color. So multiply the numbers 3 and 5 together with the command 3 into 5. So let me do in this way, 3 into 5. To have evaluate, press down enter key and MATLAB evaluates, and you can see answer equal to 15. And internally it is checking if my answer is correct or wrong. So right now it's correct. Towards the right side, you can see within the workspace, ANS answer variable and 15 value. Now task 1 has been completed. Now I can go to task 2. Now assign 3 and 5 calculation to a variable named M as shown. So for this one, I can go click on go to task, and here I can say it as purposefully I'm doing one mistake. Let me say n equal to 3 into 5. Purposely I'm doing a mistake over here just to give you a clarity. I'm saying n equal to 3 into 5, but the task says multiply 3 and 5 and assign to m variable. Let me execute. By pressing enter key, immediately it is red color and into. So it's saying your solution should assign the value to m. So in this way, if you are going to make a mistake, doesn't matter. Still, you can go back and you can retry. Now I'll make it as m equal to 3 into 5. And I'm going to press down enter key to evaluate. And MATLAB evaluates, and if it is correct, it says as correct. If it is wrong, it says as wrong. In this way, task 2 has been completed. Now I can go to task 3. So actually, there's a description. The equal sign equal to in MATLAB is the assignment operator, meaning that the expression on the right of the equal sign is assigned to the variable on the left. When you enter x equal to 3 plus 4, MATLAB first evaluates 3 plus 4 and then assigns the result 7 to the variable x. That means this training program assumes that you are very new to MATLAB. And it's a self-learning training program. If you are very new, if you don't know MATLAB, still you can use this course and you can learn MATLAB. So it's 2 hours course. It's 2 hours course. But generally it will be taking 3 hours approximately. Because for reading and everything, it will be taking certain time because you have to understand. And there is one more thing. You can leave anytime. Doesn't matter. Let me assume that for half an hour I have done, there's some urgency, I can log out. And whenever I'm getting free time, leisure time, I can come back and I can log in. And it starts from where I have left it. Just to see. So if I'm going to log out by executing task 2, task 3, I have not executed, task 2 only I have completed. Now I'm going to log out. Once I'm going to log in, I will be at task 3 only. 1 and 2 already evaluated. So in this way, I can complete my course according to my convenience, but I recommend you all to complete the course within 2 hours or 3 hours or within 1 day or 2 days. I recommend you all to complete the course within 1 or 2 days because there are following sessions which goes with the latest technology only, which is deep learning, the machine learning and all those concepts. So I recommend you all to complete on the same day. There is one more thing. As I'm going to complete, just you can see top above, it says as MATLAB on-ramp 2% completed. The amount of the percentage of the completion will be given over here, that information. So you can look over here. So once you are going to complete 100%, then you will be getting the certificate. Okay, where you can share this certificate on your social media also. That means on Facebook and so on, yes, you can share. And the students, especially, you can share your certificates to your professors so that they can know how many has completed these courses. So this is the course that is available for the complete MITS faculty, the students, non-teaching also, everyone can use. Everyone can use. Okay, say campus-wide license. So everyone can use this. Okay, so in the afternoon, we are going to do this on-ramp, which is reinforcement learning. So what I'll do is I will go and I will type down MATLAB reinforcement learning on-ramp. Reinforcement learning on-ramp. So here I'm having reinforcement learning on-ramp. And I can launch. So now you can see, as I'm launching, share the course, certificate settings. Let me click on certificate. There is a link. There's a link where I can copy and I can share to my professors where they can view. either I complete or not, or I can view this one saying as view PDF. Right now, complete only 0%. If you complete 10%, the certificate comes as 10% only. That means making sure you are going to complete 100%. And also there's a timestamp below. So there's a timestamp below. So as senior as you are, it will be good enough for you, is it not, in comparison? So that's why we recommend you all to complete these courses. Okay, let me close this course and let me click on start the course. Generally, we will not complete the courses because do you know, whenever we go to a new college over there, I have to show them. So from starting only, I have to show them. So only this video that I'm going to show, again, I'm going to stop. Okay. But as you're free, you can go ahead and you can complete this one. So I'm going to just switch on the audio.
Okay, thank you, Prem sir, for a nice session. And we have gained a lot about the reinforcement learning, and we have seen that how this reward and agent works in the reinforcement learning. So, sir has also explained by taking one examples from the MATLAB. So, candidate that you can create if your college does not have the full license of MATLAB, then temporarily we can create account in the MATLAB that will be valid for I think 1 month, and from there you can also access the online courses. Okay, so with your Gmail ID you can create your account there and log in there, and you can also get the reinforcement all type of courses, online courses, and you click on the reinforcement learning online on-ramp courses, and you can continue with that. So the next session will start by following the yesterday link, session 2 link, and we will be available at 2 o'clock, and sir will guide us that how to perform that, execute that commands related to reinforcement learning. And I think for every ramp course at the end there is a small project, so we'll look on that also. Okay, so we'll meet again at 2 o'clock. Okay, and the link again will be forwarded by coordinator Dr. Soumya Ranjan on the WhatsApp and in the chat box also. Thank you.